Right, so I've just listed down the shear force and bending moment equation. Okay, so now we're going to sketch them. Okay, we're going to sketch. So this is still simply supported, yeah. So we are going to sketch them. Okay, so this is our shear force diagram. So this is X, this is V, 0, L over 2, 2, 4, and this is L. Okay. So the shear force, we started at PL over 2, right? Or P over 2. So this is as good as our point A, our point B, and this is our point C, the L over 2. Then we go down. Okay. And then we went down by minus P over 2. Then we go horizontal. And then at point B, it goes back up. That's where we have your last P over 2. So this is your shear force diagram. Okay, so we have done this a bit when we are doing shearing stress, right? Okay, now let's look at the bending moment diagram. So this is our M. And there's also positive bending, and there's also negative bending. And I'll talk to you what do we mean by positive and negative bending later on. So this is X, this is 0, this is L over 2, and this is L. At L over 2, we have a maximum bending of PL over 4. Okay, and then if we look at our function over here, Px over 2 means it is positive slope going up, and over the other side is negative slope. And when x is equal to L, it will end up to be 0. Okay, so on the top is your shear force diagram. At your bottom is your bending moment diagram. Okay, so let me explain this diagram. This diagram has a few features that is interesting to know. Okay, and I hope when this course finish, the videos are still for you to access to the day you die. I'm not going to lock you guys out. Okay, you do other courses, you can also refer to these notes. That is the purpose of this course. Not like, okay, the course over, you cannot access any of this. No, I'm going to make it available for you so that you can earn $1 million and give me 10,000. So what you see over here, right? Let's look at the fact regarding positive moment and negative moment. Okay. So when is the moment positive, and what does it mean by a negative bending moment? Okay, it all depends on the deformation pattern. Okay, if the deformation pattern is smiling face, right, the moments will all be positive. Okay, if the deformation pattern is negative, the deformation pattern is a sad face. So that is why for this problem that we are solving, our deformation pattern is what? Smiling face. That's why I focus the moment on the positive side. Okay, this is one thing I want you to observe. First, people ask you, What do we mean by positive moment? What do we mean by negative moment? It all depends on the deformation. Okay, number one. Number two, I want you to observe this. On the shear force, right, from 0 to L/2, the amplitude, let me use a different color, okay? The amplitude is positive. Yes or no? From 0 to L/2. In the bending moment diagram, the gradient is also what? Positive. Right? Then let's look at the other side. Okay? When the amplitude is negative for the shear force, the bending moment, the gradient is also what? Negative. Can you observe that? So I will write this down, okay? When amplitude is positive in shear force diagram, gradient is positive in bending moment diagram. Okay, and then I'm being naughty down here. I'm going to copy. I'm going to paste. Okay, and when is negative amplitude is negative gradient in bending moment diagram. Okay. Another thing I want you all to observe is this. Okay, another important feature that I want you to observe is when shear force is equal to 0, okay, there is a possibility where bending moment is at its maximum. Okay, it's not equal, crosses to 0, cross 0, cross the 0. Okay. So what do I mean by cross the 0? If you look in this yellow line that I'm drawing on the shear force diagram, it crosses 0, right? If you look at the bending moment diagram, it's where bending moment is at its maximum. There is a possibility because sometimes when your structure is loaded, right, you can have crossing of 0 point in 2 different locations. So you have to what? You have to check. Okay. Okay. So now we have done simply supported. Okay, we have done simply supported. Okay. So what I'm going to do is I'm going to use this space over here. Okay, I'm going to use this space over here. And that space, I'm going to look at a cantilever beam. Okay. So this cantilever beam that we're going to look at, okay, And as I say, it's very specific to this loading condition. So this is our point A. This is our point C, right? Over here, we have a load P over 2. Okay, we have a load over there, that's P over 2. So why this is also equal to this? That is what I want to address. That why this is equivalent to this at point C. Okay, why both are the same? Right? Why is it the same? The only way for it to be the same is mathematically we can prove it that it's going to be the same. That's why mathematician is very miserable people. How many of you know your math teacher? They're miserable, right? Right? Until, why is it miserable? If and only if they can prove it mathematically, then it's the truth. Okay? If they cannot prove mathematically, they are miserable. Okay? So I know some mathematician, I also know our math instructor, miserable people. Because if they cannot prove the Super 7 number or Lotto Max number, what is going to come? They are miserable mathematically. Okay, they have to, everything is what? Math based. Okay, everything has to be math based. So look at this. Okay, so we will prove why at point C, both the cantilever beam and simply supported beam are the same at point C. Okay, now question for you: in the cantilever beam, where will the structure fail? Anyone? Point C, right? So if you have a cantilever beam, right, you force your beam down, the region where it will move, it will not fail, right? It will fail at the region that is not moving, yes or no? Right? Usually when you bend hard enough, this thing will break over here. It will not break where the point is moving, okay? So that is your cantilever, okay? So likewise, if it's simply supported, right, and then it's bent this way, we also fail at point C, at the center, yes or no? At point C. Okay, so we're going to prove it mathematically. So we know by failure analysis, at point C is where failure will occur. How about mathematically? Okay, so let's look at the cantilever beam. Okay, so we are going to do at point A to point C, 0, x to L over 2. So we do that now. This will be P over 2. This distance will be x, positive shear, and positive moment assumption. Summation of moment in the z direction at point x. Oh, no. We do static first. I'm sorry, we do y first. Summation of forces in the y direction is equal to 0. So you have P over 2 minus V as a function of x is equal to 0. V as a function of x is equal to P over 2. Okay? So we do anti-clockwise direction, summation about moment in the z direction, anywhere at point x is equal to 0. Right? So P over 2, so it's minus Px over 2 plus by m as a function of x is equal to 0. M as a function of x is equal to Px over 2. This is between point A to point B. Okay? And the distance from here to here, I'm sorry, I did not write the distance. This is L over 2. And the distance from here to here is also L over 2. And to here. Okay? So now I'd like to draw your attention to this value over here, or this equation over here. right? I want you to draw your attention over there. Okay.